We have been following 3I-ATLAS every step of the way, revealing shocking discoveries as this interstellar comet tears through our solar system. From its strange chemical signals to X-ray emissions never seen before, scientists are uncovering secrets that could rewrite what we know about objects from the stars. Yet as it races back into the darkness of space, one mind-blowing mystery about 3I-ATLAS still refuses to be solved. December 2025 and the historic flyby. December 2025 marks the most critical moment in the story of 3I-ATLAS. This is when the comet makes its closest approach to Earth, and scientists have their best and only chance to study it in unprecedented detail. On December 19, the comet passes Earth at a distance of approximately 1.8 astronomical units, which is roughly twice the distance between our planet and the Sun. Now, before anyone panics, let us be absolutely clear, there is zero danger to Earth. This is purely a scientific goldmine, not a disaster movie. Here is what makes this moment so urgent. Interstellar objects move incredibly fast, and they do not stay long. Once 3I-ATLAS passes through the inner solar system, it will continue outward and never return. This is a one-way trip. The comet comes from the void between stars, and it will return to that void, carrying its secrets with it, unless we act now. Because of this fleeting window, space agencies and observatories around the world are treating this flyby as a scientific emergency. NASA and the European Space Agency have coordinated with ground-based observatories across multiple continents. Telescopes in Chile, Hawaii, Europe, India, and Australia are tracking the comet every single clear night. Each observation helps refine its orbit and reveals how its activity changes as it moves away from the Sun. Space-based instruments are playing a massive role as well. The legendary Hubble Space Telescope is being used to place limits on the size of the comet's nucleus and to monitor changes in its brightness over time. Other spacecraft that normally observe the Sun have also captured the comet by chance, adding even more data points to track its path and behavior. But it is not just the professionals involved in this hunt. Amateur astronomers are contributing valuable observations too. Skilled observers with moderate-sized telescopes are recording precise positions and images of the comet. These observations are especially useful because they provide coverage from many different locations and times around the globe. When combined with professional data, they dramatically improve the accuracy of orbital models. Public interest has exploded through live broadcasts organized by the Virtual Telescope project in Italy. Led by astronomer Gianluca Marsi, these live streams allow people around the world to watch the comet's motion against the background stars in real time. While the comet is too faint to see with the naked eye, these broadcasts are making this historic scientific event accessible to everyone on the planet. At the same time, the United Nations-supported International Asteroid Warning Network is running a global tracking campaign. This is not about fear or disaster. It is about preparation and learning. By coordinating worldwide observations of 3I-ATLAS, scientists are testing systems that could one day be critical for understanding future visitors from our solar system. As telescopes around the world collected their data from this close flyby, scientists began to notice something unusual in the signals coming back. The visible light was only part of the story. What appeared calm to the eye was hiding powerful activity at invisible wavelengths. And this discovery is about to change everything we thought we knew about 3I-ATLAS. Latest multi-wavelength discoveries: X-rays and composition. Scientists began studying the comet using many different types of light. This approach is called multi-wavelength observation, and it has completely transformed our understanding of this interstellar visitor. Instead of relying only on visible images, researchers used infrared, ultraviolet, radio, and X-ray instruments to uncover details that would otherwise remain completely hidden. The most historic discovery came in late November and early December 2025. Space agencies confirmed that 3I-ATLAS had been detected in X-ray light. Let that sink in for a moment. This is the first interstellar comet ever observed emitting X-rays. The Japanese-led X-RISM mission observed the comet for many hours and detected a faint but unmistakable X-ray glow. Soon after, the European Space Agency confirmed that its XMM Newton Observatory also detected X-rays coming from the comet. Now, these X-rays do not mean the comet is hot or dangerous. Instead, They are produced when charged particles from the Sun collide with neutral gas flowing out from the comet. This interaction creates X-ray photons through a process known as charge exchange. By studying this mysterious glow, scientists can learn exactly what gases are present in the comet's surrounding cloud, called the coma. Early analysis of the X-ray data suggests the presence of carbon, nitrogen, and oxygen. These elements are essential building blocks of planets and, crucially, of life itself. What makes this so important is that X-ray observations are especially good at detecting gases like hydrogen and nitrogen that are extremely difficult to observe in visible light. This gives scientists a powerful new tool for studying interstellar objects. Infrared observations added another major surprise. Data from the James Webb Space Telescope revealed that the coma of 3I-ATLAS is dominated by carbon dioxide. In most solar system comets, water vapor is the main gas released as the comet warms near the Sun. But in this case, carbon dioxide appears to be more abundant than water. Scientists believe this could mean the comet formed in an extremely cold environment, far from its original star. Ground-based spectroscopy confirmed the presence of carbon monoxide and small amounts of water vapor. These findings suggest that 3I-ATLAS contains a fundamentally different mix of ices compared to most known comets in our solar system. This difference strongly supports the idea that planetary systems across the galaxy can be chemically diverse in ways we are only beginning to understand. Understanding where 3I-ATLAS came from is one of the most fascinating parts of this entire story. From the moment it was discovered, astronomers realized this object did not belong to our solar system. Its path through space told a clear and undeniable story. 3I-ATLAS interstellar journey. The comet is traveling on what scientists call a hyperbolic orbit. This means it is not bound by the Sun's gravity. It is passing through only once, and it will never return. Think about that for a second. This object has been traveling through the darkness of interstellar space for millions, possibly billions of years, and it just happens to be passing through our cosmic neighborhood right now, in our lifetime. When 3I-ATLAS was first detected in July 2025 by the ATLAS Survey Telescope in Chile, scientists quickly calculated its speed and trajectory. They found that it was moving far faster than any object that originates in our Kuiper belt or Oort cloud. At discovery, its speed was already over 200,000 kilometers per hour. As it approached the Sun, it accelerated even more. This extrinsic velocity could only be explained if the comet came from outside our solar system. By tracing its path backwards, astronomers determined that the comet entered our solar system from the direction of the constellation Sagittarius. This region points toward the dense central area of the Milky Way. However, this does not mean the comet comes from the galactic center itself. After traveling through interstellar space for such an immense time, pinpointing a specific parent star system is essentially impossible. Scientists believe that 3I-ATLAS was once part of another planetary system entirely. Long ago, gravitational interactions with large planets or nearby stars likely ejected it into interstellar space. Once expelled, it became a frozen wanderer, drifting silently between the stars. During this journey, it was exposed to cosmic radiation and extreme cold, preserving ancient material from its birth environment like a time capsule from across the galaxy. Estimates suggest that the comet may be billions of years old, possibly older than our own Sunday. This makes it a true relic of cosmic history. Unlike comets formed here, which have been altered by repeated passes near the Sun, 3I-ATLAS remained mostly unchanged until now. The study of 3I-ATLAS has never been the work of a single telescope or a single country. From the very beginning, this comet triggered one of the most coordinated observation efforts ever focused on an interstellar object. As its importance becomes clear, space agencies, international organizations, and individual scientists joined forces to track and analyze it as thoroughly as possible. The long monitoring campaigns and worldwide observers. NASA has played a central role in this global effort. The agency coordinated observations across its ground-based networks and space-based assets. The Hubble Space Telescope was used to constrain the size of the comet's nucleus and to monitor changes in brightness and activity. Hubble data helped scientists estimate that the nucleus could be anywhere from a few hundred meters to several kilometers wide. The wide range in this estimate is caused by the bright cloud of gas and dust surrounding the core, making precise measurements extremely challenging. Several NASA spacecraft designed to study the Sun also contributed unexpected data. Instruments on missions such as Stereo and SOHO captured images of 3I-ATLAS as it moved through their fields of view. Their observations added valuable information about the comet's position and interaction with solar radiation. The United Nations supported the International Asteroid Warning Network because involved as the comet approached the inner solar system. Interstellar objects move quickly and behave differently from typical asteroids, making them difficult to track. IAWN used 3I-ATLAS as a real-world test to improve global astrometry techniques and international coordination for future cosmic visitors. European observatories and ESA missions also played a major role. The XMM Newton X-ray Observatory and ground-based telescopes across Europe contributed critical data. Scientists from Asia, South America, and Africa also joined observation campaigns, making this a truly global scientific effort. This long monitoring campaign has shown exactly how modern astronomy works at its best. No single instrument can fully understand an object like 3I-ATLAS. It takes cooperation, shared data, and constant communication across borders. The lessons learned from this effort will shape how humanity responds to the next interstellar visitor, whether it arrives next year or decades from now. The unsolved mystery that refuses to be explained. Even with all the observations and data collected, 3I-ATLAS remains a source of profound mysteries. Scientists have learned a tremendous amount about its composition, trajectory, and behavior, but several unusual characteristics continue to puzzle researchers and challenge existing theories about comets. One of the most surprising findings is the chemical composition of the comet. Those infrared observations from the James Webb Space Telescope indicate that carbon dioxide dominates the coma, while water vapor is far less abundant than expected. Most comets from our solar system release water as the primary volatile when they approach the Sun. The unusually high carbon dioxide content suggests that 3I-ATLAS formed in an extremely cold environment, far from its original star, and that its chemistry is fundamentally different from local comets. This raises profound questions about the diversity of planetary systems in the galaxy and the variety of conditions under which comets can form. Another anomaly comes from polarimetric studies, which measure how light is scattered by dust and gas in the coma. 3I-ATLAS shows what scientists call a negative polarization branch that does not match what is typically seen in comets and asteroids from our solar system. This indicates that the dust particles surrounding the nucleus have unusual properties, possibly in their size, shape, or composition. Please like and subscribe channel.